Hello and welcome to the Cold Finish Steel Bar Institute's teleconference seminar on the state of the art of cold finishing. We are coming to you from teleconferencing centers in Chicago, Illinois and Pittsburgh, Pennsylvania. He was formerly with the Research Institute of the Fraunhofer Society in Darmstadt and the Institute for the Research for the Iron and Steel Engineers. He has a mechanical engineering degree from Technical University Hanover, and he received his PhD degree in 1963. Dr. Schwer?
Thank you. Gentlemen, our company Kieseling and Albrecht, Dr. Fangmeier and myself, we thank you for the opportunity to talk about bar turning and straightening. Our presentation will be based on our experience with our equipment in worldwide locations. In my report, as already mentioned, I will speak about the current state of high-speed centerless bar turning. This paper is concerned exclusively with the manufacture and application of round bright bar. Special emphasis will be placed on comparing the two processes, drawing and centerless turning, with their various advantages and disadvantages, quality characteristics and limitations. The current state of the art in Europe, and particularly West Germany, will also be briefly touched upon, and there will also be some mention of the levels of production and requirements which modern bar turners have to meet. In the following, I will refer to cold finish bar as bright steel. Let me at first speak about the main characteristics of bright steel, which is smooth, bright, and scale-free surface. Then, close tolerances, also relatively higher strength values, and free of surface defects and of decarburized outer layer when turned or ground. In general, it can be said that bright steel in the dimensional range up to approximately 1.5 inch is mainly drawn from the coil. Above 1.5 inch, turning predominates. Rough grinding has declined in importance because it is less productive than the turning method employing carbide cutters. What's now about the quality features of bright steel? The most important criteria which bright steel is required to meet are close tolerances and, to an ever-increasing extent, defect-free surface condition. The tolerances are stipulated in the ISO, the International Standard Organization. In West Germany, approximately 80% of all the bright steel turned lies within the tolerance ranges H9 and H11. The tolerance symbol H indicates that deviations are only tolerated on the minus side of the nominal dimension. Thus, for a diameter of 1 inch, the following tolerances apply. H9 means 1 inch plus 0 minus 2 thousandths. H11 means 1 inch plus 0 minus 5 thousandths. These values apply irrespective of the grade of material and are therefore subject to a different set of rules than the guide values published by the Cold Finished Steel Bar Institute, in which the material grades play an important role. By way of comparison, the next figure shows the tolerance values for certain main sizes. As can be seen, H9, that's the blue one here, provides for considerably closer tolerances, while the H11 tolerance is somewhat wider. That's the green. column. Also of significance when classifying bright steel is the condition of the surface of the material. The main features taken into account are its roughness, cracks, skin decolorization, and the surface strength properties related thereto. The surface condition is quite different, depending upon whether the bright steel has been drawn, this is a non-cutting process, or turned or ground, as this is a cutting, metal removing process. The most apparent basic advantage of turned bright steel is that all the surface defects, such as cracks, seams, overlaps, and so on, are removed by turning, as are the decarburized layers with a lower strength in relation to basic strength. As regards the individual criteria, the following can be said. Speaking about the roughness. The degree of roughness obtained by drawing depends upon the surface condition of the starting material. The usual measurement values employed to describe surface roughness, such as the peak-to-peak value and the RMS value, can only be applied to drawn bright steel to a limited extent. This is not the case with turned bar. The roughness profile obtained by this method is shown in schematic form in this figure. As can be clearly seen, the surface is made up of two components. The waviness caused by the macrogeometry of the tool and the roughness caused by the microgeometry of the cutting edge. In the form which this waviness takes, the major cutting edges and side rakes are clearly distinguished, as is the advance of the material for each cutter head rotation. The average RMS values which can be obtained lie between approximately 14 and 80 microinches. You can see it here. The subsequent straightening or polishing process carried out in a two-roll straightening machine can reduce these values to nearly 10 to 20 microinches, as you can see here. The roughness values attainable in turned bright steel mainly depend upon the material, the cutting speed and feed rate, condition of the cutting edges, and the dynamic rigidity of the bar turner itself. If the bright steel is required to be extensively defect-free, this requirement can only be met by turning or grinding, or by a combination of both. If drawing alone is applied, it is impossible to prevent surface defects in the rolled material, such as cracks, scabs, score marks, seams, and pores from being retained. Drawing only reduces the depth of the defect. The frequent requirement that the material shall be seam-free or free of surface defects can, if at all, only be met by turned or ground material. The maximum depth of seams in hot-rolled bars in Europe must not exceed 1% of the diameter. That means that a hot-rolled bar of 1-inch diameter may have seams not deeper than 10 thousandths. At the same time, 10 thousandths to 12 thousandths is the smallest possible cutting depth when centerless turning. Consequently, it can be taken for granted that seams in the hot-rolled bars are removed by the turning operation. The comments made concerning cracks also apply in general to the decarburized layer of bright steel. The depth of decarburization in cold-drawn bright bar depends predominantly on the depth of decarburization in the hot-rolled starting material. Drawing reduces the depth of skin decarborization by roughly the same proportion. For example, if you have a diameter of 1 inch, the depth of decarborization before drawing is roughly about 12 thousandths. When you have a reduction in cross-section, about 50%, then the depth of decarborization after drawing is still 10 thousandths. This means drawing does not remove the decarborized surface zones. Right bar, free of decarborized zones, can therefore only be produced economically by centerless turning. There is also a close relationship between skin decarborization and surface strength in bright steel. It is a well-known fact that with carbon contents in excess of 0.4%, decarborization causes smaller yield and tensile strength in the surface zone. This disadvantage cannot be completely compensated for by the work hardening effect of the drawing process. The next figure shows the hardness distribution over the cross-section of a hot-rolled and steel-blasted bar of 1035 grade after the various operations. For example, in the top, after turning and straightening, the center, after drawing and straightening, and in the bottom, comparison of the products finished by the two processes in straightened condition. In the initial condition, a decarborized zone of less strength becomes apparent just below the surface. You can see it here. If you have turning, that's a top diagram, the turning removes a surface layer of 40 thousandths and just work hardens a near surface zone to a depth of less than 20 thousandths. You can see it here. While straightening on the two-roll machine superimposes a work hardening effect which extends right to the bar core. The drawing, see it here, that's the bar core. The drawing, the center diagram, results in an almost uniform strength increase over the entire cross-section due to full plastic deformation with a given reduction of 12%. You see, that's the original hardness, and this is by drawing this small one. Further work hardening resulting from the subsequent straightening process is superimposed on the work hardening of the drawing process, although this occurs to a lesser extent than in the case of straightening after turning. Although the straightening machine setting was identical, the strength increase caused by straightening after drawing was less than that after turning. That is, because the material has already been work hardened during drawing. As shown in the bottom diagram, the strength pattern over the cross-section shows no significant difference irrespective of whether the 1035 grade was turned and straightened or drawn and straightened. In the case of grade 1035, the low reduction in strength as a result of skin decarborization is still fully compensated for by the work hardening rate encountered during drawing and subsequent straightening. In the case of steels with carbon content above 0.4%, things are different. As an example, in the next figure shows the plain carbon steel 1060, where the initial condition indicates a significantly lower strength as a result of skin decarborization in the depth range of 12 thousandths to 15 thousandths. You can see it here. As in the case with grade 1035, turning results in near-surface work hardening to a depth of about 20 thousandths. That's a top diagram. Superimposed on this work hardening effect is further work hardening to a depth of about 40,000 as a result of the subsequent straightening operation. In contrast, with the softer grade 1035, however, straightening has no strengthening effect on the core due to the comparatively higher yield stress. During drawing the center diagram, the strength is increased over the entire cross-section, similar to grade 1035, but again, this strengthening effect is considerably less than in the case of 1035 due to the lower work hardening rate in grade 1060. However, the reduced strength resulting from skin decarburization cannot be compensated for by drawing nor by subsequent straightening. The bottom diagram shows that at a depth of 2000s below the surface, the viscous hardness of the drawn and straightened bar is about 90, and hence the mean tensile strength some 40,000 psi below the respective values of the turned and straightened bar. The remaining section shows no significant difference, as you can see it here. This negative effect may be expected in all steels with carbon levels exceeding 0.4%, as in carbon steels 1045, 1060, direct hardening steels 4140 or 5140, spring steels 5160, 6150, 9260, and ball bearing steels 52100. Let me now speak about the requirements of bar turners and their design features. The various quality features of bright steel described in the previous section lead to certain requirements being placed on modern bar turners, which today are exclusively operated with carbide tools. The use of carbide inserts resulted in much higher cutting speeds and therefore higher productivity. An efficient modern bar turner is expected to meet the following requirements: high dynamic rigidity of the system, hollow shaft bar, also a very good damping effect. Then, high hollow shaft RPM in order to ensure maximum cutting speeds, also in case of small diameters. Readjustment of the carbide tools during turning, possibly as a part of an automatic measurement and tool feed control facility. Further, exact vibration-absorbing guiding systems close to the cutter head, short tool change times, short downtimes for size changes, and also reasonable maintenance requirements. With the aid of the sketch of a bar turner shown in the next figure, these points shall be explained. Of particular importance for the quality of the bright steel is the vibrational behavior of the machine. If chattering vibrations occur, not only will tool life be short, but the tolerances and surface quality of the finished bar will also be adversely affected. A guiding system which effectively absorbs vibrations is therefore absolutely necessary. Guide rollers of carbide alloy arranged in front and behind the cutter head in two planes in each case perform this function and are springs suspended to ensure extensive vibration absorption. Sliding pads can also be employed instead of rollers. We have been able to put forward an optimum system design with regard to pretension, damping and concentricity of the cutter head as a result of numerous practical and theoretical investigations. Of particular importance for the quality of the turned bar, apart from the guiding system, is the static and dynamic rigidity of the tool adjustment system, and of the hollow shaft drive. The tool adjustment system operates perfectly while the machine is running thanks to a conical sleeve which is moved in an axial direction, thus radially adjusting the rigid tool slides with the carbide inserts. You can see it here. Here's a conical sleeve and causing here then a radial adjustment of the cutters. The high degree of rigidity of this arrangement means that on the one hand, tool adjustment can be carried out in steps of 6/10,000ths during the cutting operation, and on the other hand ensures that the work is carried out within the required tolerances. A particularly stiff type of hollow shaft bearing is also required, as is the exact manufacture of the surrounding parts. Suitable diameter measuring devices can be employed to continuously monitor the actual diameter and compare it with the set point diameter while the machine is running. The next figure shows the main features of the hollow shaft again, and you can see that all red design, that's a hollow shaft, rotates. You can see the guide system in the yellow case, and also the wedge, the conical sleeve here to adjust the cutter. The requirement for short tool change times has been met in that the tool slides which position the tools in the cutter head are equipped with cassettes. Now it's not so clearly to see here, but this is the cutter head, this is the tool slides, and here are small cassettes. Here are the small cassettes. You can see this also here. When the tools are worn, the cassettes are simply replaced by means of a fast action locking device. A further advantage is that any type or shape of tool, as single and tandem tools, can be accommodated in the cassette. You can see here this kind of tools, then here a round tool, a triangle tool, and two triangle tools. With this system, tool change times of between 2 and 3 minutes are obtained. Of similar importance is the size changeover time. To ensure short downtimes, for instance 3 to 5 minutes, it is a must that all the elements involved cover the entire working range of the machine and need not to be exchanged. Our bar turners fulfill this requirement. Let me now speak about bar turners for maximum output. Modern bar turners operate exclusively with carbide inserts, as already mentioned. Compared with the cutting tools in normal lathes, the cutting tools for bar turners feature a major cutting edge and a long side rake. They may be a one-piece or two-piece design. In the case of two-piece design, two-piece tools, the functions of the major cutting edge and side rake may be performed by different inserts and possibly with different carbide grades as coated or uncoated. The design of the side rake is of particular importance for accuracy and surface quality, because its function is a kind of secondary cut with smoothing effect. It also carries out a kind of guidance function for the workpiece within the cutter tool plane. The length of the side rake further determines the maximum rate of feed of the machine or a certain surface quality. From experience, the maximum feed per cutter head revolution should not be greater than one side rake length. That means, as 4 cutter tools are simultaneously at work, the surface is worked in this way 4 times over. The rate of through speed throughput currently attainable in some machines already in service amounts to approximately maximum 240 feet per minute for bars and approximately 270 feet per minute for turning wire from coil to coil. Thanks to the contributions made by Kieserling to metal cutting theory in the case of centerless turning, in conjunction with numerous tests and measurements on a properly designed prototype, it is nowadays possible to calculate both the time it takes to execute a job and the attainable volume of the production. However, before we follow an example of an output calculation, one important fact must be emphasized. Currently, the bottleneck of the turning operation is still the tungsten carbide tool. There is no limit to the drive rating for which a bar turner can be designed. But if the cutting tools become burned out and have to be exchanged within a very short time, economic turning operations will not be possible. Therefore, we base all our output calculations on a theoretical tool life of approximately 1 hour per cutting clip. This having proved to be the best compromise between high output and economic operation. It has been also discovered that there's a certain relationship between the size of a cutting tool and the capacity of the main motor as shown in this figure. These cutting tool sizes with their corresponding motor sizes represent today the optimum in efficiency in centerless bar turning. As an example, when you have a size, a length of this cutter of 1.5 inch, then you can translate 45 horsepower for each cutter. This means 4 times 45 horsepower, roughly about 185 horsepower with this cutter. Our bar turners are, however, designed in such a way that they will also meet technical demands which might arise due to future cutting tool developments. Getting back to our output example, the next figure shows an output charge for a 3-inch bar turner which was produced by our computer on the basis of the material and machine characteristic data. As an example here, the attainable feed and production rates have been plotted as a function of the depth of cut for material 1045, which is best machined at a cutting speed of approximately 400 feet per minute. And here you find the rough diameter, and here you find the removal. And then you can read as an example, for a 2-inch bar, you can get a through speed when you remove 80 thousandths of roughly 50 feet per minute. The output charts can also be presented as output graph. Here you find the diameter to turn. Here you find the through speed, and you can read also the same when you have 2-inch diameter of 2 inch, and you have now here it's fixed a removal of 5% or 3%, say 4%. You have a throughput speed of 50 feet per minute. Also, you can read here the output in tons per hour you have. As an example, the same. You have 2-inch removal of 4% of the diameter. You can produce 50 tons per hour output as a 100% figure. But maybe that we shall speak about this later in the discussion. Special attention should be given to determining the installed motor rating. This should be matched to the middle cutting process. That means where large diameters and high depth of cut are required, high drive torques are necessary. This applies to the lower speed range of the hollow shaft. In the upper RPM range, where smaller diameters and smaller cutting depths are concerned, the cutting torques necessary are lower. The next figure shows these interrelationships. in the form of the performance specification of the DC drive for a Kieserling 3-inch centerless bar turner with 150 horsepower. The hollow shaft has a variable speed control range of 1 to 50 with two gear steps and is field controlled after approximately 1/6 of the maximum speed, starting here with the field control. By way of comparison, the characteristics of a 170 horsepower drive without field control has been plotted. This characteristic is similar to that of a belt-driven bar turner. As can be clearly seen, there are gaps in this drive's performance. You see here a large gap between, you can say, the same, this motor, 150 horsepower, 170 horsepower, but when you don't use field control, you have here a large gap of production rate. This, however, is even more apparent in the torque diagram as shown in this figure here. You see here the blue one is a 3-inch bar turner from Kieserling, where you have, when you have to turn large diameter, 3-inch to 1.5 to 3-inch, you have a large torque available here. And when you have no field control, you have here this small torque only available, and this is also a gap in production. The following shows now some more production figures obtained from practical in-service operations for the various sizes of bar turner. They refer to the effective monthly output per shift for a mixed range of bright steel grades and bar diameters. So, if you have a 1-inch machine using special 4-wire from coil to coil, you have a monthly output per shift of 400 to 500 tons. A 2-inch machine, roughly about 450 to 550 tons. A 3-inch machine, 550 to 650 tons. A 4-inch machine, 700 to 850 tons. And the 5-inch machine, 900 to 1,100 tons. Now at last, I would like to briefly discuss the situation concerning bright steel production in West Germany, which is also, incidentally, typical for Western Europe. The next figure shows the levels of bright steel production for the main West German manufacturers for 1976 to 81, in the dimensional range between a 1/4 inch and 7-inch. As can be seen, production remains roughly constant, around 550 to 600 tons bright steel, with approximately 1/3, this is here, 1/3 turned and 2/3 drawn. The main reason for this is that the most important dimensional range is between 3/4 of an inch and 1¼ of an inch. And this is mainly drawn. The next figure shows this and shows the percentage distribution of bright steel production for 1980 as a function of diameter. This distribution can be taken as typical. You see here the diameters, and here the distribution, the percentile distribution of the cold finished bars in Germany. This means drawn bright steel is manufactured up to approximately 2-inch, but main is up to 1¼ or 1½ inch, while turned products are starting at a 1/2 inch and going up to 7-inch and more. The next figure shows the distribution of turned bright steel according to the various steel grades. As can be seen, calm steel, that's the red figure, and alloy steels, the yellow, for approximately 40% each, while the rest is taken up by high alloy steels and stainless grades, blue, green, and pale blue and dark blue. The diameter tolerances lie essentially within the ISO tolerance groups H9 and H11, as shown in the next figure. You see here H9, the blue one, and H11, the green one. There's also a lot larger than H12. The proportion involving H8, which is practically ground quality, is very low, but can be also done with a turning machine and lies roughly about 3%. Let me now come to a summary. The machining of hot-rolled bar or wire on bar turners has continued to increase in recent years thanks to the use of tungsten carbide tools and the higher cutting performance that these can provide. The result has been considerably higher feed rates and productivity, and with developments going on at the same time in the form of improved machine design and the employment of modern drive and control technology, bright steel quality, this means close tolerances and surface conditions, has also improved. This has meant that for diameters above 1 inch to 1.5 inch, turning has almost replaced drawing in Western Europe, especially for higher alloys. In particular, the ever-increasing user demands for bright steel with no surface defects, including the requirement that the decarburized skin be removed, can only be met by turning. Although rough grinding is also possible, this is not economical enough as compared with turning. Comparing today all the methods of producing cold-finished, defect-free bars, it is evident that centerless turning employing a state-of-the-art machine is the least expensive process for diameters above 1 inch. Thank you very much for listening.
Thank you very much, Dr. Spear. At this point, we're going to turn to questions and discussion from the audience here in Chicago. Assisting Dr. Spear is Hans Winterberg, Vice President of Sales from Kieserling, and Max Meyer, President Kieserling, USA.
Would you recommend an 100% pre-straightening prior to turning then?
I think we should. A bar that is crooked does make it more difficult to really let the machine produce at the highest level possible. If you have a bar that is not capable of rolling by itself, it will interfere with automatic operation of a machine. Because in automatic feeding, you depend on proximity sensors to tell you where the bar is at. And if the bar doesn't come close to that sensor, you're just dead. It just doesn't work that way. So it is desirable to run the bar through a pre-straightener, so you don't have any hooks in there, but the bar doesn't have to be perfectly straight. That is not necessary.
Yes, we have another question.
Doherty from Bliss & Laughlin Steel. Why does peeling or turning seem much more popular in Europe than it does here in the United States?
What we feel about this is that in Europe, all people, and especially automotive, are used to make smaller sizes. That means you see that at our cars, we have smaller cars than yours. And that means at the same time, if you are downsizing, if you're sizing smaller, you have to consider better material. And if I say better, I mean to change from, for example, 1020 to the highest carbon grades, like 1045, or even going to 4140, and all these qualities. And looking at these steel qualities, everybody is requesting this quality to be defect-free. And for that reason, that happened already long ago in Europe and especially in Germany. And for that reason, we think that it had to lead, consequently, to turning machines, because this seems to be, or that is, at the moment, the only economical way of getting defect-free material.
Have we exhausted the questions in Chicago?